What's poppin', guys? Today we're going to walk through a couple of different optimization examples, and I'm actually not going to go through them step by step. I just want to give you guys an overview of how to approach them. Usually at this point in the optimization unit, I let students kind of struggle through these types of problems, so I might actually be giving you more guidance than I typically would in class, but I want to at least help you guys visualize what's happening. So the first example that we're going to look at is the open top box problem. So the open top box problem starts with a flat rectangular shape. Usually we're working with like a piece of paper or something like that. So let's just say that my piece of paper is 10 by 20 for the sake of this example. The idea is that we want to create a box. And the way we create the box is by cutting congruent squares out of the corners of the paper. Now, we don't know how big the squares can be, and that's really the biggest variable here, is like how big do we make these squares? Because depending on the size of the squares determines the size of the box that you're working with. So we cut out those squares out of all four corners, and then essentially what's happening here is you can fold up the sides. So I'm going to attempt to draw some dashed lines here to show where we're folding. So we fold up those four sides, and that creates an open top box. In class, we usually actually do this activity with a piece of paper, and we kind of make it a competition to see who can create an open top box with the biggest volume. So if you want to try that with a piece of paper, just cut out some squares and see what the volume ends up being. But you can imagine folding up the sides, and we end up with something that looks like this, although this is a pretty terrible drawing. Let me make it look a little bit more three-dimensional. Yikes. So there's my open top box. So it's an open top box. I was in trouble like 3 words into that. All right. So from here, the idea is we are trying to optimize the volume. Well, the volume is the length times the width times the height. Seems like we have 3 variables, which is certainly too many. Now the key here is that all of these dimensions, the length, width, and height, are all directly dependent upon the size of the square that we cut out of the corners. So really the only variable that you guys have to worry about here is whatever the length of that square is. You know, if that square length was 2 inches, you would know all your dimensions immediately, right? If it was 3 inches, you'd know all your dimensions immediately, because you'd be able to just subtract a couple of those lengths from the 20 and from the 10, and whatever that x value is itself, that's really just the height of the box. So your job is to create 3 different expressions in terms of the variable x. You should be able to create one for the length, create one for the width, and create one for the height. And the idea is that you start with whatever those original dimensions were. So like in my case, I have it 10 by 20. And you should be subtracting away 2 x's from each of those sides. And then the height is x itself. So I hope you guys give this one a try. The other problem that we're going to look at is the rectangle in quadrant 1 scenario. So the rectangle in quadrant 1 problem is kind of a classic optimization problem because it allows us to bring other derivative rules into the fray. The idea is that you start in quadrant 1, so I'm constructing my quadrant 1 here, and there's some sort of a function. It doesn't matter what the function is, but there's some sort of a function that is going to pass through quadrant 1. So there's my function, and I'm just going to call it y equals f of x. In the example problems that you guys see, f of x will actually be a function. I think they're both exponential in the problems that you guys see. But I just want to keep it abstract. So the idea here is that we're trying to construct a rectangle. Now, one of the vertices of the rectangle is going to be on the origin, and the other vertex is somewhere on the curve. So I've just drawn one of these supposed rectangles, and I can actually draw it out right now. So you can see an example of the rectangles we're talking about. Again, one of the vertices is always on the origin, and the opposite vertex is on the curve itself. So there's my first rectangle, and it's got some area. But it's not the biggest area that I could have created. This yellow rectangle, for example, is definitely has a larger area. So the goal here is we want to optimize area, and I'm just going to write that out, that the area of the yellow is clearly greater than the area of the red. But the whole idea with optimization is we don't want just one that's bigger, we want the biggest area that we can find. Maybe I have to try this green point way over here. This is a dramatically different shaped rectangle. Is its area bigger? I'm not really sure. What if I take another point off to the side? Let me see if I can find purple. Do I have purple on this thing? I think I have purple. There it is. So I've got some purple, and I could create another rectangle right here, and the yellow and the purple almost look the same. Is one bigger than the other? It's close. So we have to use optimization to precisely calculate the biggest area. So area of a rectangle is just length times width, or base times height. And what you guys are challenged with here is trying to figure out, well, what is my base? What is my height? And think about the way that this problem is set up. Think about the fact that it's living in quadrant 1. You can use that to your advantage. Good luck.